Maoqiang, you can start when you're ready.
Sure. Hello, everyone. Today I present a paper published in NIPS 2021, and the title is Evaluating Gradient Inversion Attacks and Defenses in Federated Learning. First, I will introduce different gradient inversion attacks. Then I will explain the defense methods. Finally, I will provide experimental results and the conclusion. Federated learning is a distributed learning manner where the client is the local model and upload the gradients only. The server aggregate the received gradients and update the global model. The clients don't share the training data, but the attacker can use the gradient inversion attack to recover the training data based on the shared gradient. This paper mentioned 4 different gradient inversion attacks. The first one is the gradient matching. Sorry. The first method is gradient matching. The attacker first randomly initialize a dummy input and the dummy label, and then feed this dummy input and label into the models and get dummy gradients. They update the dummy data and optimize the object functions, which is the distance between the real gradient and the dummy gradient. The final achieved data is close to the real training data. And the attacker is assumed to be the QoS server. This is the experimental result of the gradient matching. We can see the attacker can recover the training data, but this method has some limitations. First one is the client's training batch size is up to 8. If the batch size is larger than 8, the attacker cannot recover all the images based on this method. And also the second limitation is the image resolution is very small, it's 64 times 64. And the third one is the client cannot use the relu as activation. This is because this L2 distance cannot differentiating the gradient if use the relu as activation. The second method is use chips that extract the label. This is different between the first method. The first method, they use the randomly dummy label, but this one, they can extract the label information from the shared gradient. We can see this is the cross entropy loss, and this is the computed gradient. And the gradient can be divided into 2 parts. The GI is the gradient with respect to each of the outputs. And if the activation, for example, is used sigmoid, we can see if the label is the real label, and this part of gradient is always be non-negative. It is always negative. So we can use this method to identify the real label information. This is the performance of this method. The DLG is the first method. We can see the generated label is not always right, but this method can extract a right label. But the limitation is this method can identify the labels only if the gradients with respect to every sample in the training batch are provided. It cannot identify the batch labels. And we can see this method can converge faster in the attack compared to the first method. And this is the third method. The difference is they consider the choice of the L2 cost function and optimization via LBFGS in the first method are not optimal, especially for the more complicated model architectures. They consider the gradient magnitude appears not to be an important factor and search only for images that match the normalized ground truth gradient in direction. So they propose to use a cost function based on the cosine similarity and minimize the loss only based on the sign of its gradient by using the atom with the step size decay. This is the performance comparison between this method and the first method. We can see that the first method works well for the shallow and smooth model architecture. But if for a conventional architecture, the deeper, the reconstruction quality degrades significantly. But while using the cosine similarity as the cost function, the attack performance is better in the event for the deeper model, for example, the ConfNet or the RaceNet 20. This is the fourth method. The fourth method has some difference. The first one is they can extract the labels of whole batch. We can use this example. The M is the feature, is the feature, and the N is the output, and the K is different samples in the batch. We can see when we summarize the feature, and the gradient can show that if the label is if the output is the real label, and the gradient value is always negative. And also we can see that the magnitude the value is always larger than others. The output is not right label. So even the gradient is averaged, we can still identify the label in this batch. But this method has the limitation, which it assumes there are non-repeating labels in the batch. So they consider this assumption is reasonable at some data sets such as the ImageNet when the batch size is always smaller than the number of classes. The second difference is they use the batch normalization information as the regularization. Here they use three regularization. The first one is regularize the total variance of the input. The second one is regularize the L2 norm of the input. And the third one is they use the regularize the batch normalization. By using this difference, the method enables recovering image from a larger batch compared to the third methods before, and they can recover the large batch images and for large network such as ResNet 50, and on the more complex data set such as ImageNet, and the resolution is higher, which is 224 times. And this paper analyzed the 4 different methods and find out that they have 2 strong assumptions. The first one is some method assumes that the batch norm statistics information is known. If the batch norm statistics information is known, the attacker can apply the same batch normalization used by the private batch on his recovered batch to achieve a better reconstruction. But this information is not always necessary in the be shared in the federated learning. So the assumption is too strong. And the second assumption is knowing or able to infer private label. However, if multiple images in the private batch belong to a same label, neither approach can tell how many images belong to the label, let alone which subset of images belong to the label. So under this setting, the assumption is not available. And this paper evaluate under the 2 relaxed assumptions. We can see that when attaching a batch of 60 low resolution image from the CIFAR-10 dataset and recover a single high resolution image from the ImageNet dataset. If they know the exact batch normalization information, they can recover the image better. But if the information is not available or part of available, the recovery performance is worse.
Maoqiang, can I ask a question? So
okay.
For the current inference attack, what's their assumptions? They assume they know the private label, or they assume they don't know the private label?
Which one? In the...
I mean, for the general one, when we talk about the inference attack, right? What's their assumption?
For the inference attack?
Yeah.
What? For the inference attack, they also don't know the private label, in my opinion.
They only know like this paper, they know the batch norms, the statistics, or they don't know anything. I mean, when we talk about the attacker, we assume the attacker is strong, right?
Yeah. You mean the normal attack or the attack in this paper?
I mean, for the general one, it's not the inference attack in this paper. For the general one, we assume the attacker know all the labels, right?
No, they don't know all the labels. The first method, they just use the dummy generated label, but in the following the three methods, they can infer the label information according to the gradient. But they assume that each sample in the batches have a different label between each other. So this exam shows that when in a batch there are some samples have the same label, the attack performance will be worse.
Okay.
Because the attacker cannot identify which sample has the they can identify the exact label of the sample if there are some samples have the same label.
Oh, okay. Move on, please.
Okay. So this figure shows that for CIFAR-10, when the batch size is large, many images in the batch belong to the same class, which essentially weakens label restoration. So under this setting, if the private label is unknown or can be inferred because, as I mentioned before, the attack can only know how many labels in this batch, but if there are some samples have the same labels, the attacker cannot identify the exact label information belong to each samples. So the attack performance will become worse. But this is the real condition in the real world. And this paper introduced some defense method. The first one is the encrypt gradient. For example, use the secure aggregation methods, but these methods always require special setup and can be costly to implement. And by using this method, the curious server can still launch the gradient inversion attack on the summed gradient vector. And also, if the attacker is the curious client, they can still launch the gradient inversion attack on the model returned by the server. So this time of the defense method is not always available. The second defense method is perturbing the gradients. For example, the gradient pruning. the first paper, the first method, they have do some experiment to evaluate the gradient pruning method. We can see that when pruning more than 70% of the gradients will make the recovered image no longer visually recognizable. And we can also add in noise to gradient, for example, the differential privacy. But in the experiment of the first method, a successful defense requires adding high noise level such that its accuracy drops by more than 30% on the CIFAR-10 dataset. So when use this defense method, it will influence the test accuracy so much. And the third defense method is to encrypt the inputs. For example, the mix-up trains the neural networks on composite images, create via linear combination of image pair. It has been shown to improve the generalization of the neural network and stabilizes the training. And the second one is the install height, which is when after the mix-up implementation, it adds another layer of security. It picks a random sign flipping pattern and output the encryption, where is coordinate-wise they flip the 50% sign randomly, and here this is the coordinate-wise quantification of factors. After that, the neural network is trained on encoded images, which look like random pixel vectors to the human eye and yet lead to good classification accuracy. In this paper, and the perturbing gradient method only measured in the first method before and after the three methods to improve the attack, they have no measure the defense's performance. So in this paper, the authors compare the defense performance between the gradient prune and the mix-up and the insert height, the three defense methods and their combination.
So Maoqiang, I have some doubts. So what's the purpose of this paper? I mean, I think mix-up and install height or whatever, the students in our group present this paper before, right? We already discussed that, and our conclusion is, yeah, it seems you cannot extract things from there, but there is no theoretical proof for that, right? The simple mix doesn't mean theoretically you can show, okay, certain kind of piracy can be guaranteed, you cannot derive any kind of a feature or any kind of information from the mixed results. Although they show some simple proof, but it's not like rigorously cryptography proof, stuff like that, right? For pruning, it's more like empirical. We don't say any kind of this say, okay, I do the 70% of pruning, you can show me some theoretical results. Nothing like that, right? That's the reason why people still prefer, gradient perturbation approach, like we add a DP noise or something, because we can have some quantified, provable results. What kind of a privacy can be guaranteed, stuff like that. I don't know why they want to do this. What's the final purpose for this? You only want to show something, say you reconstruct cannot be recognized by human eyes?
Yes, the three method can have no the quantified level as the differential privacy. They only show the trade-off between the defense performance and the test accuracy of the model. But these have no the theoretically proof. They only do the experiments.
What do they mean by worst case leakage and average case leakage? What do they mean for this?
Average case leakage is the LPI-PS matrix. When this matrix is higher and shows the similarity between the similarity between the real image and the recovered image. So when this metric is higher, and the defense is poor, and the
Okay.
average means
how is that similarity? What's the metric for that similarity? You do a pixel to pixel comparison, or you do any kind of classification results comparison?
I think it's a pixel emulation, and average means the matrix of the average in the batch, and the worst case means the worst one in the batch.
I really have doubts for this one. I'm not sure if you 100% capture this paper, right? So why you want to compare the pixel to pixel similarity? Because if you talk about the similarity, you want to evaluate the performance, you already have a computer, right? So the final purpose is you do the classification to say, okay, it's a horse, it's a dog, it's a cat, right? With some new image, right? If you launch an attack, you reconstruct the picture. What's the purpose of your reconstruction?
Because if the because if this value is higher, that means the recovered image is more similar to the real trained image. So they
yeah. If it's pixel to pixel, it's not necessarily means that from the feature point of view, is the same number, right? I mean, pixel to pixel, you can be probably significantly different, but after you do the learning model, the feature you extracted probably is very similar. I really feel confused. Also, for all this defense mechanism, I don't think they propose anything new, right? So all these three category of defense mechanism is already there.
Yes, but these two methods, the previous work didn't measure these two methods to define the gradient inversion type before.
Because they're not proved. Yeah, they published paper there, but they're not proved. I think I didn't remember, probably Jia Hao presented this paper before. We argue with each other a lot for this paper, right? My opinion is not theoretically strongly proved.
Yeah.
So you cannot say, okay, you can defend the inference attack or inversion attack or whatever, because it's only show, okay, empirical result, but it's not theoretically proved, mathematically proved, right?
Yes.
Hey, Dr.
No.
The case is this paper. You can see the title or the whole step or like related works. Maoqiang have introduced is they try to focus on a kind of attack is called a gradient restriction attack. So they introduce different like the previous paper with different assumption, and but under the case, they first introduced like I will answer your first question. First question is like what's the assumptions before like other the general gradient restriction attack, right? The first one, there are many assumptions. The first one is do we need like a batch normalization statistics, which like the batch normal statistics include like the information of the average of the some like the image or the previous batch information. So do we use this statistics or not? And also the second one is do we consider the defense method, for example, add noise, add sparsification, add clipping, grid clipping, or add the insta head. And the third one is do we consider different batch sets? For example, the only one batch set, that means only one sample in each derivation, and like much easier, right? Or how about if we consider like a batch set like for example 32, and the third one, the fourth is do we consider local steps? You know, federal learning, they consider like many local steps, like 1, 2, 3, or like there is some numbers, right? Local steps. Maybe one local step is much easier, right? And also the next one is do we consider private labels, or can we use some method to infer private labels? So current method, just like Maoqiang said, like the current method to infer private labels is still it still has challenge to deal with the case when multi images appear, right? So the next one, they try to consider on another paper, they consider, do we need a public dataset? The public dataset may be used to train a GAN or train an encoder to better extract the information from the local the recovered image or something. So this is a general assumption.
What do you mean is their purpose is they try to study the things from the attacker point of view, right? How can I successfully reconstruct the gradient or launch this kind of gradient attack under different kind of condition or assumptions?
Yes. But you know, the case is because some previous papers, they require some different assumptions, right? They try to consider that if we relax some assumptions, that their attack method is still useful. So they in the first several like previous several like PVT, they also show that it's somehow not quite useful but quite practical, right? It has some challenge. And then in this page, they consider like how about if we consider different like a defense method, for example, gradient pruning, mix up or insta head, right?
But still, they cannot be called some defense method.
Yeah, they call in this kind of paper.
I have doubts for that. Yeah.
No, like this is what we this is somewhat different, but they call it a defense method to deal with a gradient or adversary attack.
Okay. Okay. Yeah. From another point of view, I mean, from another perspective, it shows the mix-up and inter-inster-hide, they are not secure, right? They cannot protect the privacy because under those assumptions, you can still launch the attacks. But I agree with you. Yeah, I'm not that comfortable to call them defense master, but I don't know. It's more like heuristic. It's not like, it's proven, everybody can accept the defense masters, right? But I don't know why they don't show the differential privacy performance here. Even use the homomorphic encryption. We know that from the output, they can still launch the reconstruction attack. They didn't do that. They only pick up the easy case and do the experiments, right? So
yeah, actually they have some argument to say that like DPS is introduce a lot of accuracy loss.
That's true.
Some they just include that.
Yeah, but they're private. For all of this, the only thing you can argue, they're not private. They're not good approach. So I'm not saying they should not do this, but at least you need to add the DP approach there. You need to add the homomorphic encryption over there, right? To say, okay, under different cases, still, I don't want to call it a defense method, but I will say on different masters, under different algorithm, I can still launch the attack, but the performance is like this and this and this. Which one is better, which one is not, right?
Yeah, I understand the point, but this is recording, but it's fine. I can say because they have the authors of this paper, they have like a different like a conflation or like a bad discussion or argument with the DP peoples.
Mm-hmm.
So maybe they just to try to do not consider the DP method and in their paper is so the DP the people familiar with different price will not read this paper. Maybe I just guess. You remember the discussion, right? I showed you before the DP community with this guys, right? And maybe this paper actually because like the ISTA had won the the Bell Lab Prize, right? Second place for Bell Lab Prize, and they also try consider challenges, the restructuring challenges to show like you can do that.
I know there is a lot of discussion and even arguments for the Eastern hat. Many people say from a cryptography point of view, their background cannot allow them to agree with this kind of an Eastern hat design, right?
Yeah, and also some like several attacks method already proposed to deal with Eastern hat, but they don't acknowledge that. They said that they need some like a much more like a computational power or something, or like computational
that pushes back our discussion into the Eastern hat again. I don't want to discuss that, but again, if you call this defense approach, right, you need to show the experiment performance under all these approaches. It's not like you pick up the easy one and you give up the difficult one, right? So that's my point. Even I can agree with you. Okay, this paper is more from an attacker point of view. Say, okay, under this assumption and that assumption, I can successfully launch the attack. Yeah, I agree with you. But still, when we talk about the defense approach, you cannot just give up the most popular, everybody agree on this kind of approach, but you just pick up some questionable, easy approach to do the evaluation, right? So that's the reason why I feel it's not that convinced for this kind of thing.
Yeah, you are right about the case. You can see the figures. It looks so blurry, right? When they consider another different, they call different.
Again, you know, it looks blurred. It doesn't mean anything, right?
Yeah, I know. So
in particular, if you guys study machine learning, blur doesn't mean anything. Yeah. Yeah, you do the adversary sampling, do this and that, you do the GAN. Blur doesn't mean anything. Blur is a blur. We're just you know, blurred by human eyes. We're just a fool by human eyes. You need to show, okay, it's blurred by the machine. That's the things we want to know, right?
Yeah, you are right. I understand.
Yeah, even you add a random noise, it blurred, right? It blur doesn't show anything. Anyway, I have some consideration for this one anyway. Okay, Maoqiang, please continue.
Okay. We can see that if without defense, when batch size is 1, the attacker can recover image well from the gradient. Increasing the batch size make it difficult to recover well, but the recover images still similar to the original one. And when used the gradient pruning, in the first paper, they pruned the percentage 70%. They can defense well, but in the more but in the following the attack method, only pruning percentage 70% no longer safe against these attacks, and they need to prune the higher than the 90% can have a variable defense performance. And when use the mix up, if use the mix up alone, may not be a practical defense against the gradient inversion attack. But if combine the mix up and the pruning, for example, the pruning percentage is 90%, it will be a more better defense performance. And we can see when the batch size is 32, okay, with batch size is 32, the install height alone also cannot defend these gradient inversion attacks. When the batch size is 32, combine the install height with the pruning, makes the reconstruction almost recognized unrecognizable. And these two figures shows the trade-off between the defense performance and the model test accuracy. If this value is higher, means the defense performance is better. We can see the combination of the install height and the pruning. We can see the install height defense method will be a better performance to trade off the defense and the model accuracy. And this table shows the when the attacker used the gradient inversion to recover one single image, from the different data size of the client's data set. And we can see that when use the install hide as the defense method, the attack needs much more times to recover the image. So here are some conclusions. The first one is using the batch norm layers in the network, but don't share the information of the batch norm layers. This will improve the defense against the model inversion attack. And the second one is using a large batch size will weaken the attack. A batch size smaller than 32 is not safe, because when the batch size is larger, the more samples in the batch may have the same label. And the third one is combining multiple defenses may achieve a better utility and the privacy trade-off.